Okay, in this video, I'd like to share with you some more techniques in using the T-chart method to complete unit conversions. In prior videos, we were talking about converting units of the same type of measure into another. This time around, we will be using multiple units of measure simultaneously. And by that, I mean something like this. In this particular example here, we've got Lance Armstrong who's riding a bicycle at 32 miles per hour. For any of you that are taking Mr. Miser's physics class, you might recognize that a lot of times rates of speed are measured in feet per second. And so it'd be nice if we can convert that. Now, I know that sometimes using Google or other technology might be available to you, but let's see how that can be done using traditional mathematics. So I'm going to start off with 32 miles and 1 hour as the beginning of this T chart. As we had yesterday, or the last time you watched one of these videos, you'll note that I'm just writing down what was given to us first, and I'm trying to create a T chart that contains elements that will cancel along the way. Now, ultimately, I need to get miles into feet. So we've got a distance of miles, and I'd like to convert that into feet. So that's actually not too hard to do because we've got a unit conversion that allows us to do that pretty easily. And in 1 mile, we have 5,280 feet. Now, unlike prior examples, we now have two units in our T-chart. We have both feet and hour left over. So if I complete the multiplication in this T-chart, I'm going to be left with a unit of measure not in miles per hour, but in feet per hour. And that just won't do because our goal is to get to feet per second. So now I'm going to focus on what I can do to make this hour unit of measure turn into seconds. So since I want this hour to cancel out and disappear, and it's in the bottom, I'm going to write it up top over here. That's, again, the nice thing about this T-chart is that if an element is written in the bottom of the chart and the top of the chart, they'll eventually cancel. They don't have to be right next to one another to cancel. And I know that in 1 hour, there are 60 minutes. Now here again, if I complete this T-chart and multiply the top rows together and the bottom row elements together, I would end up with feet per minute. And that's, again, not quite what we're looking for. So I'm going to take this one step farther and change minutes to seconds with a minute measurement on the bottom and a minute measurement on the top. I know that those two units will cancel, and I know that in 1 minute there are 60 seconds. So this T-chart here will allow us to convert from miles per hour to feet per second. So let's go ahead and do that math. Remember, across the top, across the numerator, the top row of this T-chart, we'll multiply all these numbers together, and that's just 32 times 5,280. That looks like 168,960, 168,960, and our unit across the top is feet. And across the bottom, we'll multiply 1 times 60 times 60. So 1 times 1, of course, is 1. Times 60 gives us 3,600. And across the bottom, we have a unit this time. So I'm going to go ahead and list seconds across the bottom here. And we're not quite finished here. We should go ahead and divide those two. 168,960 divide by 3,600. And it looks like he's traveling at 46.93. So we'll call this 46.93 feet per second. And since the picture is coming into view, hopefully you all picked up on the joke that I posted in Schoology this week. No, I'm not going to be driving a Butler Tech mobile classroom to visit you during the week, but I came across this old lesson from last year, and I found this picture of me driving one of Butler Tech's semi-trucks. For those of you that don't know, I was a dump truck driver for 5 years before I became a math teacher. I worked for the Department of Transportation, and I do have my commercial driver's license for that reason. Um, I had an opportunity one day to visit the folks at the Adult Education Center for Butler Tech, and I drove around their semi trucks for part of an afternoon. So that really is me driving one of their trucks. So thought that was kind of fun. Thought I'd share it with you while we're here on home instruction. Anyway, moving on. This conversion seems a bit more appropriate because here we are talking about a horse that ran in the Belmont Stakes in 1973. This horse is very famous, Secretariat. And during this race, this horse covered 12 furlongs in 12 minutes and 24 seconds. And unless you are familiar with horse racing or this unit of measure, that doesn't mean a whole lot to most people. We would like to know, well, how fast was that horse in miles per hour? With this additional unit conversion here, I think we can make this happen. Now, before we get too far into this, I am going to make a special note here. 2 minutes is the same as 120 seconds. That's something that we should be able to convert in our head. 60 seconds in a minute, so 2 minutes is 120 seconds. We add to that the 24 seconds on top of the 2 minutes, and we're now looking at 144 seconds is the length of time that it took for Secretariat to complete this race. So with that in mind, I'm going to go ahead and write this down here. I'm going to say that Secretariat covered 12 furlongs in 144 seconds. Now, you could have turned this into a decimal, 24 divided by 60, and gotten the decimal and said Secretariat covered that distance in 2 point some odd minutes, and that would be fine. But either way, it's nice to have a single unit of measure for time so that we can make our conversions as we go. Now, again, our goal is to get into miles per hour. So the first thing that I'm going to do, and order doesn't really matter here, but the first thing that I'm going to do is I'm going to try to change this furlong measurement. I don't really know what that means, but evidently one furlong contains 660 feet. And as long as I start building my chart this way, I know that the furlongs will cancel. And my goal is to get to miles per hour, so I'm now going to convert feet into miles. If I place feet in the bottom of the T-chart, then I know that's going to cancel with feet from the top of the T-chart, and there are 5,280 feet in 1 mile. So this T-chart is set up right now to give me in miles, an answer, I should say, in miles per second, but again, that's not what we're after here. So I'm going to add to it this notion of, well, there are 60 seconds in 1 minute, and I'm putting the seconds on top this time to cancel with the seconds on the bottom down here. And one more conversion to complete the work. We have 60 minutes in 1 hour, and I'm doing that because I need this minute unit to cancel with that minute unit. And now we're left with hours in the bottom, miles on top. So after I complete the math for this T-chart, I'll have a measurement in speed of the horse in miles per hour. So across the top, we have 12 times 660 times 1 times 60 times 60 again. And we're getting quite a large number here. 2851200. So that's 28,512,000 miles. And across the denominator, we have 144 times 5280, which is 760,320 hours. So, what's interesting about this is that the rate of speed that we're going to reduce to is also equivalent to this large fraction. At the rate that Secretariat was running, he could cover or travel 28 million miles in 760,000 hours. That doesn't mean a whole lot to us, so we go ahead and do the final division. 28,512,000 divided by 760,320. And after we do that division, that looks like it's 37.5 miles per hour. And that to me seems pretty quick. So let's go ahead and try our next problem here. A patient was instructed to take 500 milligrams of this medicine every 4 hours. So we have 500 milligrams for 4 hours. And you'll notice as I'm building this particular T-chart, I'm going to abandon this horizontal line. I'm just going to use the lines on my paper to keep track of that. We would like to know how many grams of this medicine was consumed over 5 days' time. So let's go ahead and complete that conversion. We'll change milligrams to grams, and we'll change hours to days. Based on the unit conversion chart from day 59, hopefully you're still referencing that. We have 1 gram that's worth 1,000 milligrams. So I want milligrams in the bottom of this chart to cancel. So we now have grams that I'm after. That part of the conversion was pretty easy. Let's now change hours into days. Well, again, that shouldn't be too hard. There are 24 hours in one day. So after I complete the multiplications in this T-chart, I'm going to be left with grams and days as my unit of measure. And 500 times 24 is 12,000 grams. And 4 times 1,000 is 4,000 days. So this person would consume 12,000 grams in 4,000 days, but that doesn't help us out too much. So we'll take the 12,000 divided by the 4,000, and we have 3 grams per day. Now, of course, this person is taking medicine for 5 days, so if this patient was taking 3 grams per day, we could simply multiply by 5 days. 3 times 5 is 15 grams in total. Now, one other thing that I'd like to point out with this T-chart is that we could have actually completed this conversion that I've written in blue over here right at the same time that we were doing right at the same time that we were building our T-chart from before. So again, the idea about these T-charts is that we build them so that we get units to cancel. And an additional measurement in this particular problem was that we were taking this medicine for 5 days. Now, if I write 5 days across the top row of this T-chart, then this day unit will cancel with this day unit, and the only unit that remains is grams. Well, that's exactly what we were looking for in this problem. How many grams were consumed? And so we can complete the math. 500 times 24 times 5 is 60,000 grams. And across the denominator, 4 times 1,000 is again 4,000, but there is no more units along the bottom here, and that's okay. 60,000 divided by 4,000 is 15. So again, the 15 grams that we saw just a second ago are produced by using just a T-chart. Now I know this video is getting a little bit long, but we've only got 3 questions left, so I think I'd like to just push through and just finish up this lengthy video so that it's all in one shot. So here we go with number 13. A car travels 1 mile in 1 minute. So let's let's see if we can convert that real quickly into something more meaningful to us. If we travel 1 mile in 1 minute, we could complete the conversion. There are 60 minutes in 1 hour. So let's see here. Minutes are going to cancel. Multiplying across the top is 60 miles. And across the bottom, we have 1 hour. So 1 mile per minute is 60 miles per hour. To travel 1 mile in 40 seconds, by what percentage must the car increase its speed? Okay, well, that's kind of interesting. Let's now travel 1 mile, only this time in 40 seconds. So let's make this quick conversion. There are 3,600 seconds in 1 hour. Now, this is a conversion factor I've just picked up on by multiplying 60 um, minutes per hour times 60 seconds per minute. It always ends up being 3,600. So when we multiply here, the seconds will cancel, and we're left with 3,600 across the top and 40 across the bottom. 3,600 divided by 40 is 90. So if we convert 1 mile per 40 seconds, that's actually the same as 90 miles per hour. And so we're increasing from 60 miles per hour at the beginning, 60 miles per hour at the beginning here, to 90 miles per hour. The question is kind of tricky, but it asks what percentage must the car increase its speed? Well, with one more side note, I'll point out this, that percent change, and this is something that's discussed in the math for tech class. Percent change is equal to the net change, or the amount of change, divided by the original number. And so the net change in this case is an increase of 30 miles per hour. We're going from 60 to 90. So in this case, we're increasing by 30 miles per hour, and our original speed was 60 miles per hour. And so if we take 30 and divide it by 60, 30 divided by 60, we're left with 0.5. 0.5. And 0.5, when you move your decimal 2 places to the right, turns into 50%. So that car must increase its speed by 50% if it's completing 1 mile per minute and would like to complete 1 mile in 40 seconds. That's a 50% increase in speed. Now, hopefully you're seeing some value in these T-chart unit conversions. While these situations or scenarios may not apply to you or to any of your labs, for some of you they will, but others they may not. But at least you can see the value in this one technique, this T-chart technique, and how many different types of problems it can actually address. So let's go ahead and finish up these last two. The foundation of a building requires 346 cubic yards of concrete, and the concrete is hauled in buggies that hold 9 cubic feet each. How many loads are required to pour the foundation? Well, whether you're studying construction or not, you might become a manager someday or a consultant, and this could be a typical problem that you might have to address. How many loads or how many buggies are necessary to complete or to carry the amount of concrete necessary for this particular building's foundation? So let's start with what we know. 346 cubic yards per foundation. So I'll just say one foundation. Not a typical unit, but it's what we've got. There are 346 cubic yards needed for this foundation. So let's see, how about we convert yards into buggies? Now, I know that each buggy can hold 9 cubic feet, but the problem was given to us in cubic yards. So let's go ahead and convert cubic yards. And real quick, this I don't believe is a measurement that's on our conversion chart. No, I'm not seeing this anywhere. Cubic yard to cubic feet or anything like that. Okay, so let's just think through this for a second. A foot, or I'm sorry, a yard is 3 feet wide. So if I make a cubic yard, that would be like 9 square feet on the front of this face, but now the face has to be 3 units deep as well. So if I had 1 square representing a square foot, then 3 by 3 by 3, that's going to represent how many cubic feet fit into 1 cubic yard. So 1 cubic yard contains actually 27 cubic feet. So that's going to allow us to convert from cubic yards per foundation to cubic feet per foundation. We also know that there are 9 cubic feet per buggy. So if there's 1 buggy and 9 cubic feet, then I know that these 2 units will cancel. And now we're dealing with buggies per foundation. And that's the solution that we're after. We want to know how many buggy loads that it will take to pour this foundation. So across the top, we need 346 times 27 times 1. That's 9,342. So 9,342 buggy loads. And across the bottom, we need 1 times 1 times 9. So that's 9 foundations. If we had multiple buildings to to construct here, we need 9,342 buggies, and that would complete 9 foundations, but that's not really what this question's asking. So I need to take the 9,342, divide it by 9, and we're left with 1038, 1,038 buggy loads. Now you could easily imagine, hopefully, that this problem could be converted if we're ordering trucks of concrete. I don't know exactly how much concrete a truck can hold, 2 or 3 yards, or maybe 8 yards, something like that. Um, Instead of asking how many buggies are necessary to complete the foundation, we might change that to um, how many concrete trucks are necessary to order for a particular job. Okay, and so this last one looks to be perhaps the most complicated, but with a little bit of thought, I think we can get through this. A steel railroad track expands this amount, a very tiny amount of inches for every inch of length for each degree of increase in temperature. So we're talking about thermal expansion here. The steel railroad track extends or expands in length or size as the temperature increases. Now, if a steel rail is 32 feet long, we want to know how much does that 32-foot length section change due to a change in temperature. Perhaps the winters get down to 20 degrees below zero and the summers get up to 110 degrees. Now we're talking surface temperature of the railroad, so even if the air isn't 110 degrees, it might pick up ambient heat and radiant heat and increase to that temperature. So if you've ever looked at a railroad track, you'll notice that there are these expansion joints built in to allow for this, to compensate for that. And somebody had to plan for it. Somebody had to design this into the railroad system. So let's see exactly how much a 32-foot section of railroad track expands. So I had to pause the video here to set this one up first, and this is kind of interesting because our unit in this case is this 0.0000636 inches of expansion for every inch of length per degree of change. And admittedly, this is starting to get a bit complicated, but let's try to just keep this in mind. The railroad track expands this much for every inch in length that the track is, and for every degree that the temperature changes. So that's the expansion. This is the unit that we're beginning with. So the first thing that I'm going to do is I'm going to convert this inch in length to feet in length because our problem had 32 feet of railroad track. So I know that there are 12 inches, and I'm going to be real specific with my units here, 12 inches of length per foot, and then there are 32 feet in this particular problem. 32 feet of length of track, that is. So my inch length will cancel with this inch length, and feet will cancel with feet. And I'm also going to note here that 20 degrees below zero is like negative 20 on a scale, and 110 degrees above zero is like 110, and the distance between negative 20 degrees and positive 110 degrees is a change of 130 degrees. And I would like to get this unit to cancel in the denominator. So with degrees in the denominator, I'm going to include an extra section of this t-chart to indicate that there's 130 degrees of change in the numerator, and that's going to cancel as well. And now, well, I could put some placeholders here just to help keep our math straight. But now when I look at this t-chart, the only unit that remains is this measurement here, the inches in expansion length. The inches in track length or degrees in temperature have all canceled. And so now all I need to do is multiply the top row together, and across the bottom row, there should have been a 1 here, across the bottom row we've got a bunch of these 1s. So there's no real effect on that denominator whatsoever. And so if I multiply this decimal, 0.0000636 times 12 times 32 times 130 leaves me with this decimal, 0.317. And by reviewing the units that were in our t-chart here, I know that this is 0.317 inches of expansion across a 32-foot section and a 130-degree swing in temperature. So I think it's safe to say that if our steel is going to endure those temperature changes for every 32-foot section, we should be prepared to allow for 0.317 inches of expansion. For extra credit or bonus opportunity, let's say this, 0.325 inches is equivalent to what fraction? Some of you will know that right off the top of your head. So you'll know what the fractional expansion ought to be approximately in 0.317 inches of expansion. So for those of you that stayed with me during the entire video, thank you for that. Good work. And for everyone else that checked along or popped in time to time, hopefully these explanations help you a little bit and give you an idea of how you can use these T-charts moving forward. Thanks for watching.